That will be fine. Maybe I can have the lights above me off so that you can see better the board. Turn off the lights above me, yes. Okay, that's good. That's good. Okay, I'm not sure what they say, but anyway. So this is the sound. In order to understand what happened with the discovery of quasi-periodic materials, let me take you back to the Let me take you. Batteries can help. Let me take you. It's okay. It's not a big deal. Let me take you back to the mid-80s. In the mid-80s, the mid-1980s, there were 3 surprising discoveries on the structure of matter and its properties. And I hope you understand my English. Okay, that will be great. And they came year after year, these 3 discoveries, and all of them received the Nobel Prize, year after year. So let us start. The first one was my discovery, and this is the paper that I published with friends in 1984. But the discovery was made in 1982, and I will tell you the story of the discovery later on. This was the year 1984. 1985, fullerenes were discovered. Fullerenes are, or also is known as buckyballs. These are molecules, globular molecules, like sphere, like balls, made of carbon. And this was the beginning of nanotechnology as we know it today. And a year later, 1986, high-temperature superconductivity was discovered. Now, high-temperature superconductivity was known since 1909. It was discovered well over 100 years ago. But everybody thought that superconductivity could exist up to a temperature of about 30 degrees Kelvin. That's very low temperature. And then when Bednorz and Alex Muller discovered high-temperature superconductivity, it means that now you can have superconductivity at temperatures of liquid nitrogen. Then everybody, of course, was happy, and there was no rejection or any objection to the discovery. When fullerenes were discovered, same thing. Nobody objected it. There was a little bit of a few papers which said, no, this is not the right model, but that died very quickly. But when quasi-periodic materials were discovered and announced, they met a lot of resistance from the top of the scientific community. And this is the story of my discovery, and this is the story that I'm going to tell you today. But in order to understand my discovery, I will start with very simple terminology, so that all of you will come out with a lecture and will say, now I know something about quasi-periodicity. So in order to do that, let us start with periodicity. We'll talk about order, about periodicity, and about rotational symmetry. We will start with order. Here is a 2-dimensional lattice, a planar lattice of atoms, and clearly you see that there is order here. What does it mean? It means very simple, that if I ask you to continue this drawing in this direction, or in this direction, or in any other direction, you know how to do that. It's very simple. You measure this distance, you put it here, another one here, another one here, and so on and so forth. You can continue in each and every direction because you understand the order. That's enough about order. Now, what about periodicity? If you look in this direction, the red direction, you see that there is not only order here, but also periodicity. The distances are equal. And in each direction that you go, such as in this direction, there is periodicity, and in this direction there is periodicity. In every direction that you go, the distance from here to here equals the distance from here to here, and so on. This is periodicity. Now, in this lattice, the motif, as we call it, is one atom. One atom here, and so on and so forth. What about rotational symmetry? Here we have rotational symmetry, and I will show you how you can rotate this lattice. I just added a little handle. plate handle here, so that you see when I rotate it what happened. So I can turn it 90 degrees, and it looks the same, except for the little handle. 180 degrees look the same, 270 degrees look the same, and 360 degrees look the same. I can do it 4 times, 1, 2, 3, 4, and every time it looks the same. So this lattice has a 4-fold rotational symmetry. Okay, here is a picture of a fence in the hotel that I stayed in Easter Island. Easter Island is a remote place in the Pacific. And this is the fence of the hotel. Why am I showing it to you? Because here we also have periodicity. But the motif is not just one thing, not just one bar, but more than that. Look here on the left. You see, this is the motif that repeats itself. Large, large, small, small, large, large, tiny, small, large. And again, large, large, small, small, large, large, tiny, small, large. So this is the motif. It's not made of one element, it's made of several elements. And it repeats itself periodically. You see? Periodically. One after the other. This is the larger motif. In real life, in crystallography, this means that large molecules can also repeat themselves periodically. Okay, now let's have a few examples of rotational symmetry. Look at these drawings. This card has a 2-fold rotational symmetry. You can turn it 180 degrees and it will look the same. This has 3-fold rotational symmetry. This flower has 5-fold rotational symmetry. This pizza has 6-fold rotational symmetry. This is a motif. And a motif can have any rotational symmetry that you want. Okay, now let's say a few words about crystallography. I don't want you to read what I've written there. The story is more interesting than what is written there. People in the past, in the far past, in history, were interested in crystals. They found crystals in nature, and they made crystals in their primitive laboratories, and they saw that the crystals have facets, and the facets have angles between them. And they imagined that the reason for the facets is the fact that crystals are made of very small particles called atoms. And atoms are arranged in such a way to create these facets. This is why crystals had those faces, and there were angles between the faces. And they measured the angles and imagined what is the structure, what is the internal structure, where are the atoms sitting there. But they had no way to prove it. It was all an idea, but no experiment to prove whether they were right or wrong. In the year 1912, this is 102 years ago, a scientist named von Laue performed the first X-ray diffraction experiment. Now, X-rays, and we have a famous doctor here, are used to look at fractured bones, and to look at not only fractured bones, also at bones that are not fractured, and also internal part of the body. This was used after the invention of X-rays by Dr. Röntgen. This was in 1895. But from 1895 till 1912, 17 years, nobody knew what X-rays were. People used them, but they didn't know what they were. 1912, von Laue showed in one experiment that X-rays have a wavy nature. They are electromagnetic waves. And he showed also that crystals have indeed an ordered structures, as people thought before, because he performed the first X-ray diffraction experiment. So this is the history of crystallography, and a year later, after von Laue, the father and the son, Bragg, from Leeds in England, they invented the Bragg equation. It's a very simple equation that explains us how to solve diffraction patterns. How can we look at the diffraction pattern and tell something about the order of atoms in crystals? This happened 101 years ago, in 1913. So last year we should have celebrated 100 years to crystallography, but we didn't. Why didn't we? Because UNESCO didn't have money to do that. They have the money this year. So this year is the year of crystallography. And recently, the Israeli stamp makers, or the office of the who issues stamps, issued a stamp to celebrate the year of crystallography, and my discovery is on the stamp. It's a beautiful stamp, 10 shekel stamp. Too expensive. Okay, so based on the observations of von Laue and his followers, and I must tell you that the crystal that von Laue looked at was not only ordered, it was also periodic, such as the one that I have shown you, with periodicity. In all the crystals that have been studied from 1912 until 1982, for 70 years, hundreds of thousands of crystals were studied, and all of them were ordered and periodic. And consequently, based on these multiple observations, the definition of a crystal was something like this. So here is the definition of a crystal from one of the books, X-ray diffraction by quality. A crystal is a solid composed of atoms arranged in a pattern, periodic in 3 dimensions. Simple. A crystal is made of atoms which are ordered and periodic. Because there was no exception. All crystals that were studied were ordered and periodic. Nobody expected anything else to happen. And here is one more definition. Same meaning, exactly same meaning, but different words. Atoms in crystals are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Many words, exactly the same meaning. A crystal is ordered and periodic. And the science of crystallography was a peaceful science. It was a mature science. Nobody expected any breakthroughs. Nobody expected any shockwave in the science of crystallography. Now, here is a book by Kittel, Charles Kittel. We studied solid-state physics from this book, and I have marked something in green. I know you cannot read it because it's too small. This is why I enlarged it for you. And now we can. And he says the following. We can make a crystal from molecules. And a molecule is a combination of crystals, a group of crystals. For molecules, which individually have 5-fold rotation axes. Each one of them can have 5-fold rotation axes. But we should not expect the lattice itself to have 5-fold rotation symmetry. This was the wisdom, and everybody was happy. Now, why is it that 5-fold rotation symmetry is forbidden in periodic lattices? Here is a story. When I was a student at the Technion, I took a class in crystallography, and in the final exam they gave a few questions that I had to solve, and one of the questions was, prove that 5-fold rotation symmetry cannot happen in crystal. It's forbidden in crystal. Prove it. And I proved it. And I passed the exam, and this is why I'm here now. Let me show you one solution to that question. So, in order to prove that, let us assume that 5-fold rotation symmetry is allowed in crystals, in periodic crystals. So, if it is allowed, I take 2 atoms, P, atom P here, and atom Q, and I now make Q run around P 5 times, and P goes around Q 5 times, and let's see what happens. But in order to prove, I have to choose the 2 atoms, P and Q. They are the closest atoms in the lattice. So the distance between them is the smallest distance between any 2 atoms. There are no other 2 atoms closer than P and Q. This is how I choose it. And now let's rotate it and see what happens. So here is Q. Oh, this R is the minimum distance. Here is Q, and it starts to go around P 5 times. And if 5-fold rotation symmetry is allowed, then there should be a Q prime atom there. Now let's take P and have it run around Q. 2, 3, 4, 5. And there should be a p prime atom here. But clearly you see that the distance p prime, q prime up there, this distance is smaller than r. But this cannot be because I chose the two closest atoms in the lattice. Here's the proof. I passed the exam. Okay, so now we know that in periodic lattices, in periodic crystals, 5-fold rotational symmetry is forbidden. But there were no other crystals than periodic crystals. So the rule was no 5-fold rotational symmetry in crystals. This was what they taught me and my colleagues. Now let me show you how atoms in a crystal look like. These are atoms, and the picture was taken by high-resolution electron microscope, such as the one that we have at the Technion, and we have several more in Israel, and of course many in other countries. So this is a carbon atom, here's another one, another one, another one. Each one of them is an atom. And clearly you see that this lattice, this is diamond, yeah, is ordered, there is order there, and there is periodicity. And there is periodicity in this direction, the yellow direction, and in this direction, and in this direction. In any direction, there is periodicity. And the order, I read now, the order of carbon atoms in diamond is periodic. The allowed rotation symmetries are 1, 2, 3, 4, and 6. 5-fold rotation symmetry, as well as any other symmetry. Beyond 6 is forbidden in periodic structures. So now, let me show you a diffraction pattern. Up to now, we talked about the real space. We live in real space. Well, most of us live in real space. And crystals also exist in real space, as opposed to another space, which I will talk about in a minute. A diffraction pattern such as this does not exist in real space, it exists in a reciprocal space. Reciprocal space is a mathematical concept. We invented a mathematical concept in order to understand what we see. These are not atoms, these are diffraction spots. In the electron microscope, what you do, you take a specimen of any material that can exist in vacuum and make it very, very thin. So we make it very, very thin. How thin? Well, 100 nanometers is good. That's very thin indeed. And have an electron beam go through the specimen. Let's say that my hand is a specimen. An electron beam comes and goes through the specimen. Because the specimen is so thin, the electron beam can go through it, and it will hit a phosphorus screen. Phosphorus screen is like the screen on your mobile phone or the screen on your television, and it will make a spot in the center. And this is the spot in the center. What are the other spots? The other spots are diffraction spots, because the beam also diffracts. It goes in different directions, and it marks all these spots. So this is the transmitted beam, and all the rest are diffracted beam. This is an electron diffraction pattern, and it allows us to understand the structure of the lattice. Now, this diffraction pattern was taken from a periodic lattice, and it is also periodic. Look here. See, in this direction, in this direction, in this direction, there are periodicities in each and every direction. So, there is, now I read on the left, there is periodicity of diffraction peaks in the reciprocal space. The rotational symmetries that are allowed are 1, 2, 3, 4, and 6. No 5-fold rotational symmetry, and nothing beyond 6-fold. All this was crystallography up until the year 1982. And then something amazing happened. The International Union of Crystallography, this is the body that governs what is right and what can exist in crystallography. They are like the Latin Synod. I mean, these are hardcore people. These are no-nonsense mathematicians, mathematical crystallographers. I mean, everything must be defined from the very basics. And they have decided to change the definition of a crystal. And this is the new definition. And the new definition reads like a poem. What? The International Union of Crystallography? These hard-core body of mathematical crystallographers write poems? What's going on? Well, this is a paradigm shift in crystallography. Let us read it, and I will show you how soft the definition is. It's a poem. Let us read it. It says the following. It doesn't say crystal is. No. It says by crystal we mean any solid having an essentially discrete diffraction diagram. Not discrete, essentially discrete diffraction diagram. And by aperiodic crystal, we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. Soft, very, very soft definition. This is a crystal now. What happened? Well, what happened is my story. And now we can start my story. Up to now, it was introduction. 1982 was the 70th birth of crystallography. Remember, von Laue, 1912. 1982, the discovery. And this is the year that quasi-periodic crystals were discovered. In order to show you what happened in the day of the discovery, I will take you to my logbook. And here is the lesson to your student. When you make an experiment or any other thing which is important to remember later on, write it in a logbook. Because you think that you will remember what you did, you may remember it for 1 week, and then you forget. And you must remember it, because sometimes, just sometimes, a page in the logbook can become extremely important for your career. And this is the page in my logbook that made a difference in my career. And it contains a lot of information. I must apologize. The page was not meant to be seen by anybody else but me. These are my notes for myself. So the handwriting is sort of sloppy. And, and it's shorthand. I will explain to you. First, the date. You see on the right-hand side, at the top, it says April 8, 1982. This was the day. Nice day outside. I am in the electron microscope room. Material that was studied and noted and written on this particular page is aluminum 25 weight % manganese. It's an alloy of aluminum and manganese. So, and the numbers here are the number of plates. I take a picture, this is the number of the picture, that's all. So picture number 1720, SAD is selected area diffraction. It's the diffraction pattern, like the one I showed you. And another one, and then I take 28K means a picture with magnification 28,000 times. In the electron microscope, you have capabilities for high magnification, and this is because the electron microscope has a very high resolution, and you want to match the resolution of the microscope to the resolution of your eyes. Right? So a microscope can see the resolution of modern microscope is about 1 angstrom, which is 1/10 of a nanometer. The resolution of our eyes when we are young and happy is about 0.1 millimeter, 1/10 of a millimeter, and the magnification has to bridge the distance between what the microscope sees and what we see. Okay, so 28 times 1,000 times magnification, 17 times, and then I take picture 1724, and I look at it. I will show you this picture. I look at it and says, that's odd. Now, when Archimedes discovered something interesting, he jumped out of the bathtub and shouted, "Eureka!" But nowadays, scientists do not jump out of the bathtub. They're not shouting "Eureka." They say, that's odd, or that's interesting, and this may be a discovery. Something unexpected, something new, unexpected. This may be a discovery. So I look at it and I say, there's no such animal, like the joke. And then I take the diffraction pattern and I write 10-fold, because it has 10-fold rotational symmetry. Impossible. So, let me show you the picture. And then I continue to perform more experiments to find out what it is. Everything was on the same afternoon. It was in the afternoon of April 8, 1982. In the morning, I worked on another island. So this is the discovery, right there. So this was picture 1724, and let me explain to you what you see. You see, this is one crystal. And here is another one. Here is another one, another one. This is a polycrystalline material that is made of many crystals. Most most useful crystals, such as metals that you use every day, are polycrystalline. Like the stand of this camera is made of steel. It is polycrystalline. It has many, many tiny little crystals in it. So what's special about this picture? Well, look here. You see, this one is pitch black, and this one is pitch black. Pitch black. It means that the transmitted beam doesn't go through. It diffracts heavily. All the beam, most of the intensity that doesn't go through, it goes to the diffraction pattern. And I've never seen anything like that before. So I said, that's interesting. What is the diffraction pattern? So I take the diffraction pattern, and here it is. I look at it, say, wow, what's going on here? First of all, what is the rotational symmetry? Start to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, cannot be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I write in my own book 10-fold. Very strange. But this is not the only thing that is strange. You see, look here. Periodicity disappeared. If you take the distance from here to here, multiply by 2, there's nothing here. Take the distance from here to here, multiply by 2, you get here. And there is nothing there. So, no periodicity, 10-fold rotation symmetry. That is very, very strange. Okay, later on it turns out that this diffraction pattern is 5-fold rotation symmetry, not 10. But in order to do that, I had to perform another experiment, and I didn't do it on that day. So it's not on this page. It's called Kikuchi line pattern. But the fact is, forbidden rotation symmetry and no periodicity. Very strange. So I said to myself, okay, what are these? What can it be? And I thought that these are twins. And I will tell you in 2 words what they are, and I will not elaborate on that. The ratio, by the way, of the distance, if you take this distance from here to here, and divide by the distance from here to here, you get the golden mean, which is a Fibonacci number, which is an irrational number. I just said something I shouldn't say, because if you divide A by B, you cannot get an irrational number, but close enough. So this is it. And here comes the Fibonacci number, and I will tell you about Mr. Fibonacci de Pisa later on. Tau, or phi, called also the golden mean, and it's about 1.618 and many, many digits after that. Endless number of digits after that. 1994, I went back to the Technion. By the way, the discovery was made while I was on sabbatical at NBS, National Bureau of Standards. I'm sorry I did not mention it. I was there for 2 years, and the discovery was made there. I spoke about the discovery with my colleagues there. Nobody could come up with an explanation. But when I came back to the Technion in 1984, Ilan Blech, who was a professor here, he joined force with me and designed a model, a physical model that could explain how these materials would form. And together, we sent a paper for publication. And this is the paper, the Shechtman-Blech paper. Now, the Shechtman-Blech paper was ill-fated because we sent it to a Journal of Applied Physics, and they, those days, we scientists could not type. We did not have computers. We had secretaries, and the secretary typed. We wrote our papers by hand, and the secretaries typed it, and then printed it, and then they gave them to us, and there was no memory. If we had made correction, they had to type it again from scratch. So they did time and again and again and again and again until we said, okay, fine, now I can send it. So, and in order to send the paper out, I don't know, many of your scientists say, that today, in order to send a paper, you just type it on your computer, save it as a file, and send the file by email or another such way to the journal. And then in 1 second it is there. Not those days. Those days, I took an envelope, put the printed paper inside, sealed the envelope, stamp. I wrote the address in as nice handwriting that I could imagine, and sent it. And 3 weeks later it came back, and the editor said, Thank you, Dr. Shechtman, for your contribution. However, we decided in the editorial board that we are not going to send it for review because it will not interest the community of physicists. Why don't you send it to a metallurgical journal, they suggested. So I did. So again, I took another envelope, stamp, another, sent it to another journal called Metallurgical Transactions, and they accepted it and published it. But they published it 8 months after I sent it. In the meantime, in the summer of 1984, I went back to NBS, where I made a discovery. I went there every summer. And then I met John Kahn, who was my host, and I showed him the paper and I asked him, why do you think it was rejected? John read it and said, oh, you know, why don't we do something totally different? Let's publish a paper which is just your observations from the very first days, no model, and send it for a quick publication in Physical Review Letters, which is a very quick publication journal. We did that, it was accepted and published, and so the second paper, which is this, was published first, up before the first paper that was sent. Anyway, and the names are Shechtman Blech, the originals, and Denis Gratias is a scientist from France, who was invited to join force with us, and John Kahn. When this paper was published, it was in this November 12, 1984, it's written down here, hell broke loose, because from all over the world, I started to get email and telephone numbers, and you know, Danny, we have it, this is fantastic. And before long, an eminent group of avant-garde, excellent scientists came out and formed a large community of people who studied quasi-periodic materials. They took my discovery and turned it into a fast-growing science. So this is what happened after the publication. Now, let me explain a few things. I called my discovery, I called the material that I discovered the icosahedral phase, because it had icosahedral symmetry. So what is an icosahedron? This is an icosahedron. This particular one is made of wood, it's just a picture that I took. And it has, as written here, 6 5-fold axes. What does it mean? Imagine that you put your eye at the top and look down. You see it has 5-fold rotation symmetry. If you look from where you look, it has 3-fold rotation symmetry. You can turn this to be here, and then this to be there 3 times. It has 3-fold rotation symmetry. My diffraction patterns had icosahedral symmetry, and this is why I called it the icosahedral phase. In order to better understand an icosahedral symmetry, let me take you back to the football field. And if you look at this football, you clearly see that this is how football is built. It's made of patches, pentagons and hexagons. So I said football, the girls' league. It has, so you see 5-fold rotation symmetry, very clear. 2-fold here and 3-fold here, rotation symmetry. Football also has rotation symmetry, and I doubt that football players know that they play with icosahedral symmetry. Now I want to explain to you something about quasi-periodicity, because I discovered quasi-periodic materials. So what is quasi-periodicity? Okay, here comes an explanation. And in order to understand that, I will take you to Pisa in Italy in the turn of the century, between the 12th century and the 13th century. And Leonardo Fibonacci di Pisa lived there, and here he is. It's a drawing of him, and this is a statue that is on his grave just behind the inclined tower of Pisa. He was the greatest mathematician of his time, and maybe 500 later he was still the greatest mathematician. And in order to understand quasi-periodicity, I will show you the experiment he suggested with rabbits. These are called the Fibonacci rabbits. Here are the Fibonacci rabbits. And here is the story. In the first month, up there we have one female rabbit. In the second month, she gives birth to a little one. In the third month, the mother gives birth to another little one, and the little one from the second month matures before it can reproduce. These are the rules. every month, every mature rabbit gives birth to a little one, and every little one matures in the next month. These are the rules, that's all. So now that you understand the rule, you can continue this. For instance, let's go from here to here. So, this mother, here she is, gives birth to a little one. This little one matures. This mother gives birth to a little one. This mother gives birth to a little one. This little one matures. This mother gives birth to a little one. This one matures, and so on and so forth. That's it. The numbers on the left are the number of rabbits in every month. So in the first month we have 1 rabbit, in the second 2 rabbits, in the third month 3 rabbits, in the fourth month we have 5 rabbits, then 8, then 13, then 21, and so on and so forth. These are called Fibonacci numbers. 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 8, 13. 8 plus 13, 21. How many will we have here? 13 plus 31, 34. And then 21 plus 34, 55, and so on and so forth. These are Fibonacci numbers, and now that you know the rule, you can continue this forever. What is special about Fibonacci? Why is it related to our story? This is because there is no motif of any size which repeats itself in this structure. Let's look at the last row. By the way, I stopped here because this is the end of the page. I couldn't continue. Let's see. Large, small, large, large, small. Large, small, large, large, small, but large, large, small, large, small, large, large, small. There is no motif of any size which repeats itself. Yet, there is order. What does it mean? It means that you can continue this forever because you understand the order. And there is no periodicity. This is a quasi-periodic arrangement of rabbits, in this case, in one dimension, along the line. What about 2 dimensions? 2 dimensions is Penrose tiles. Roger Penrose is an eminent mathematician living in our time in England, and he designed 2 tiles with angles 72 degrees and 36 degrees. There are 2 rhombi. When you join them together, you can make, and you do it properly, you get the Penrose pattern. This pattern is ordered, but not periodic. There is no periodicity whatsoever here. There is no motif that repeats itself periodically, any size. This is quasi-periodicity in 2 dimensions. What about quasi-periodicity in 3 dimensions? These are my crystals. And here is a crystal of the system magnesium, zinc, cerium, and you can clearly see the 5-fold faces here, beautiful 5-fold. And this crystal is very small. This is 2 microns from end to end. So the whole crystal is about 3 microns in size. Why am I saying that? Because later on you'll see that it was very important for the recognition of quasi-periodic materials. Okay, we should skip this because this is a little bit high mathematics, although we have a good mathematician here. This will be given to him in private. We can skip that, and we'll tell you the story. And the story is about the years of rejection. When I started to talk about my discovery, the reaction was mixed with the people around me. The reaction was mixed. John Kahn, my host, said to me, Danny, this material is telling us something, and I challenge you to explain what it is. This was good encouragement. But on the other hand, my group leader came to my office one day, smiling sheepishly, putting a book on my desk, a book of X-ray crystallography. And he says, Dr. Shechtman, you know, what you're talking about cannot be. Why don't you read this book and you understand that what you're talking about cannot be? And I said to him, you know, doctor, I don't want to mention his name. I know this book. I teach at the Technion. I don't have to read it. I'm telling you, my material is not in the book. Mm-hmm. How long? 2 minutes? Okay, I'll take 5. Thank you.
Because of the crystal.
Right.
Asymmetry.
Okay, so, and the feeling around me was sort of heavy. You know, many people rejected me. If you want to see how I felt during that period of time, it was something like that. Okay, this period ended with the publication. 1984, I was not alone anymore. And you would think that everybody will agree now? Not so fast. Because the International Union of Crystallography said, bring us X-ray diffraction. Don't bring us electron diffraction. X-ray diffraction, we believe in X-ray. And we could not do that because our crystals were too small for X-ray diffraction. And it took 3 years, and only in 1987, my colleagues in France and Japan made large enough crystals. We had beautiful diffraction patterns like this. I showed it in the meeting of the International Union of Crystallography, and when I showed it, they said, okay, Danny, now you're talking. And they formed a committee that redefined crystal. Better definition of the paradigm shift in crystallography. But that was not the end of the story. Up until 1994, I had Professor Linus Pauling, the most eminent chemist in the United States, and the father of the American Chemical Society. He wrote the books, he explained so many things, eminent scientist, no doubt. And he said, Danny Shechtman is talking nonsense. No quasi-crystal, just quasi-scientist. But he was wrong. And this continues for 10 years, from 1984, 1994. In 1994, Dr. Pauling died, and that was the end of the argument. Okay, I will finish here. And I want to thank you very much for inviting me here. And for the sake of time, thank you.